Welcome to my 10th video in this lectures of magnetic circuits. Now I'm going to show you what is hysteresis. And if you didn't watch my previous videos, we did some examples, I did some lectures, and all of those examples were with direct current. Now, with DC voltage. Now, what happens if we bring on a magnetic circuit? Here we have a coil wounded on a toroid, and what happens if we bring a sinusoidal current to this coil? Sinusoidal like this. So it's not a perfect sinusoidal wave, but you get the point. Now, ideally, we had this. Sorry, I'll just use a better marker. Now, we had some pH characteristics before that looked like this, something like this. So here is the p-axis and here is the h-axis. So this was the pH character, the magnetization curve, and for example, this is on the plus side like this. So naturally, it would be good for us that this it was a odd function, that if we had a negative magnetic field intensity and the magnetic flux density, it will go something like this. And this would be the path that goes like this and this. Well, that's not the case with alternating current. This would be an ideal situation, but that's not the case. Now I'm going to show you how magnetic field intensity and magnetic flux density, or magnetic induction, how do you say it, act when you have a sinusoidal or an alternating current on the magnetic circuit. Now, here on this toroid, we have an induced EMF, a number of turns which is equal to capital N, and alternating current, sinusoidal alternating current. So here is the magnetization curve, and I'm going to show you how this acts. For example, let's take that this magnetic circuit, before bringing this current, was unmagnetized. So there was no fluxes, fields, magnetic formulas, nothing. So this was the magnetic flux here was zero. So now you bring an alternating current, small I. So here we have an I-axis, and here we have the time axis. Now, I1 and minus I1 are the amplitudes in this case. Now, how does it magnetize? So, here we said that this magnetic circuit was unmagnetized, so we start from this point 0. We don't have no magnetic field intensity, and we don't have no magnetic flux density. So here we go. So this current rises to point I1 right here, and this magnetic. And here we have on the magnetization curve, it goes like this, something like this, from 0 to point A. So we have magnetic field intensity rising to H1 to this point, and it goes to this point A. So it goes to here, from 0 to A. We have the next situation. Now, as you can see, the alternating current is decreasing and going to 0. Now, naturally, if it was an ideal situation, it would go from A to 0, but that's not the case. Now, if you have from I1, that current goes from I1 to 0, here is 0, then you have a magnetic field intensity that is equal to 0. But the magnetic flux density is not 0. It goes from A through B and to this point C. And this is a phenomena that is this is an alternating current phenomena. So when it goes here from to 0, the magnetic field intensity, we have magnetic flux density B in the index R, and this here is called a residual flux. So BR is called magnetic residual flux density. So now when the current is 0, the magnetic circuit here is going to have a residual magnetic flux density that is equal to BR. So this value varies from various types of magnetic circuits, but this is this here curvature here like this that goes from here to here is same for every magnetic circuit. Only the values are different. Now, if this, when I worked in some company and I was in first grade in my college, I saw in the company I saw that a machine passes a current through a magnetic circuit, and the engineer told me that this magnetic circuit is acting like a permanent magnet. So that's how you make permanent magnets that were not magnets before magnetizing. So if this point goes to saturation and you pass a huge current through this coil and then shut down the voltage and no current, you will have a residual magnetic flux density. So you have a permanent magnet without passing a current through it. So that's how some permanent magnets are made. Now, if you want to demagnetize this magnetic circuit, you have to pass a current in the opposite direction. So from 0 to some point here, I don't know. Here, this is the point D, from C to D. Now you pass a current in the opposite direction and you have magnetic field intensity that is equal to minus Hc. So in this point, when you pass a current minus Hc, you have a magnetic flux density that is equal to 0, like here. So now you have a magnetic flux density that is equal to 0. This minus Hc is called, sorry, my English is bad, but I think it is called coercivity. Or coercive force. So when you came to this minus Hc, this magnetic flux density is equal to 0. So now the magnetic circuit is demagnetized. Now if we go here to minus H1, which is the amplitude of this sinusoidal current, you will get minus B. Oh no, sorry. You will have a magnetic flux density that is roughly even with this value over here, just in the opposite direction. So first you had B maximum for H1 in this direction, and then you have minus B max for minus H1. So now you have the same, roughly the same intensity of this magnetic flux density, but in the opposite direction. Now this is the same situation. Now if we go from here to minus I1 to 0, from here to here, then you have a residual flux density in the opposite direction. So if you went from minus H1 to 0, then you will still have flux density in this magnetic circuit, but in the opposite direction. Now we went from here to here. Now if we magnetize the coil, it rises to this point G. So here we have a coercive force, but in the plus direction. So if you bring Hc to here, then the magnetic flux density is 0. And we have some cycles here. Now from this point, it doesn't go from here to here, it goes from here to here, this magnetization curve. This A prime and A secondary are not in the same point, but these here, A prime and A secondary, are closer together than A to A prime. So after several loops, this will go to the same, several cycles of this current, it will get together. It doesn't go here from 0 again, so this is a starting point, and then you will never have this magnetization curve if it was magnetized, that will go again here. So it goes something like here to A prime, it goes here, we have BR but little smaller, it goes like this, it goes like this, and you will have this cycle, and eventually this will go to the same point after several cycles, and here at the same E will go together. This point will go together. So this, as you can see, you have lagging. The magnetic flux density lags with respect to magnetic field intensity. So as you can see, it goes here to 0. When H1 goes here, this magnetic goes here, we have a magnetic field intensity that is equal to 0, but we have a magnetic flux density that is equal to this residual magnetic flux density. So this magnetization, this magnetic flux density lags, it's late with respect to the magnetic field intensity. And this lagging is called hysteresis. And this is very important because the surface of this area is the power loss due to the magnetization of these magnetic circuits. And now I'm gonna show you how. And after several cycles, all this will go to the same point after several cycles, and here it will go to the same point, and here and here. And then you have these hysteresis loops. And they vary to material. Now, as an engineer, you want these loops to go higher and they want to be thinner. So you don't want to have a large, these are hysteresis loops, and this is the hysteresis. This is a phenomena that which I explained, that this magnetic flux density is late it lags with this magnetic field intensity, and you want to have a thinner area and a higher area, so as much as possible if you are an engineer. So here, this surface here is the losses due to magnetizing these circuits, and this is very important with AC machines. Okay, and yeah, so this is hysteresis. I hope you learned something new, but I think you already studied this in fundamentals of electrical engineering, but here is the reminder of that lecture. So yeah, that's it for this video, and see you in my next video.